All right. In the interest of not getting too far behind schedule, I think we'll start and let people join as they go. So I'm going to find somewhere on these large screens the share button. There we go. I'm going to take over that share, and hopefully you'll see a slide there. Oops, says, and then it just disappeared. There we go. So welcome back, everyone, to MaRDA 2026. A couple of quick things. First, we had some really interesting sessions yesterday. I want to thank everyone for that. The shared notes and the question docs today have moved on. We've got session 3 and session 4 today, as well as the poster session. So there are the short links. Those will be shared in the chat, and we'll also share the full link for those who aren't allowed to use Bitly or have that blocked in some way or some form. Um, and I want to highlight again that we have new working groups coming along. Actually, if you go to the MaRDA-alliance.org website, there's a link to working groups, and that's been updated to list these 3 new working groups. For those who are interested, you can express your interest in the Google Docs during any of the sessions, and we'll dig that out. But also, you can always email info@MaRDAalliance.org. And we're going to try to populate those quickly. There's actually a plan that this summer we will do 2 in-person events to work on various aspects of at least 2 of these working groups. We'll try to have one of those coordinated with another meeting in August, and we'll have details on that coming up. We actually have the ability to provide some funding for travel for students and others who'd like to be involved who can't fund it other ways. But reach out to info@MaRDAalliance.org to find out about joining a working group. And then today, we'll start with session 3 in a minute. I'm going to pass this over to Ale Strachan, who's on the council and, of course, from Purdue. And he's going to give us an introduction to AI for materials manufacturing in the panel discussion about that. There's another poster session today. Hopefully that went well for everyone. I enjoyed the new platform myself, 4Waves, found it really easy to navigate around. That'll be from 2:20 to 3:30. It's really important to support the students and postdocs and go to those posters. I know everybody likes to step away from a meeting, but we've given it enough time this year that we hope people can see more posters. And then we'll have awards for best posters tomorrow in the last session, including a monetary prize. But the top 2 posters, one from student, one from postdoc, also get to present briefly their work to the group. So that's a lot of fun. And then we'll have a second session this afternoon on academic perspectives of labs of the future that we're looking forward to. That'll be moderated by Caitlin Jones from NIST and Kyle Sleeby from Georgia Tech. So without any further ado, then I'm going to hand this right over to Ale Strachan and let him take us off onto the session 3, the first session of the day. Thanks, Ale. You are muted. It's the first one of the day. It's good to get it out of the way.
Yes, I was just trying to model bad behavior so no one repeats what I did. So, welcome everyone to day 2. This is the 4th annual meeting, okay? And I'm super happy with what MaRDA has accomplished, and the fact that we're here 4 years after the first meeting is, I think, an amazing testament of what we've accomplished as a community. I remember when we were discussing how to capitalize MaRDA, right? And now we're in our 4th annual meeting, now endorsed by Madonna, okay? So living in the material world. So session 3, the panel I'm going to moderate, we have a stellar lineup of panelists from industry, okay? And what we want to address are the goals and gaps for industry. You might remember yesterday we also had an industry panel. That panel focused more on developers of AI and developers, people that are trying to push the boundary of how we use AI. The questions today are going to be more focused on how we use AI and turn it into products that benefit society, okay? And I'm going to let all the panelists introduce themselves and start with opening remarks. we have a few sets of questions that we're going to go through, and then we will open to questions from the audience, as we typically do. So maybe Corinne wants to take over and take over the screen and start with her introduction and opening remarks.
Well, good afternoon, good evening, everyone, wherever you are. It's a pleasure to be here. I'm Corinne Lipscomb. I'm an R&D director at Solventum, which is the healthcare arm of 3M. We were spun out about 2 years ago. So best known across medical, surgical, and dental markets for a range of products ranging from IV dressings and surgical drapes to negative pressure wound therapy devices and dental composites. So today I lead a team of data scientists, computational engineers, and data engineers to help us solve problems across these businesses at Solventum. So while we have data science capabilities, we tend to apply models, not build new ones within our workflows. And I'm happy to be here and answer questions as we go. Maybe I'll turn it over to Joseph next.
Thanks, Corinne. So my name's Joseph Montoya. I began my career a long time ago studying catalysts in a parallel plug flow and CSTR Birdie reactors for selective hydrogenation of epoxy butene. But most of my research training has actually been in chemical simulation for catalysis and later on, more generally, for material science. I consider myself a software engineer, actually, a field which, of course, is being radically transformed in real time by agentic coding tools, for better or worse. My current role is as the research strategy lead for the Toyota Research Institute, which, as my title suggests, is a very research-heavy role, much like Corinne's, but with the focus on Toyota's core business of automotive manufacturing and a particular emphasis on vehicle electrification and all the materials problems associated with that, and also on creating new business opportunities for the Toyota Group outside of their traditional core competency. So I think generally we are in a crisis of relevance for AI and material science, which in my view stems partially from the crisis of relevance associated with atomic simulation specifically, which much of our academic efforts in AI have really focused on. But I also think there's incredible potential for the technology. So I'm excited to chat about that and to hear other people's opinions too. Thanks. I'll pass it to, I'm sorry, can somebody suggest somebody to pass it to?
Let's go to Alex, please.
Thank you.
Is
Oh, yeah,
Alex?
I'm not seeing Alex in
Yeah.
the meeting currently.
How about let's go to Jennifer and we can reach out to Alex and see if she's having trouble with the connection.
I'm not seeing Jennifer either, unfortunately.
I think this was on the agenda, the panel at 1:40. So I think we all thought there was half an hour of something ahead of that. So perhaps they're not here yet.
The online agenda has a magic 30 minutes.
Oh, there's a gap. Oop, that's a typo. Oh, that's where the discussion starts versus the panel starting. Yeah. Sorry about that. That didn't get caught. Why don't we go ahead with some questions now for what we have?
Yeah, we can start there, and then if maybe you guys can email them and see if we can catch up. All right. So for Joseph and Corinne, so I guess the first discussion is where is industry at in terms of using data intensive methods and AI, how they're using it, what you guys are using that you can share with us. And one interesting distinction is we've always used data, right? All your companies have always been data driven, needless to say. So what's different? And Joseph mentioned, that there's a crisis. So maybe we can discuss that a little bit.
Yeah, since I said that, and since you called me out on that, I'm happy to go there. I think one of the toughest things, at least that we're finding at Toyota, is really finding ways to translate all the things, all the amazing things, quite frankly, and the things that nobody thought AI could do, but all the things it can do, into something that really does drive the frontier forward in technological development. A lot of what I work with specifically is chemical simulation and how AI can be used for chemical simulation. And as most of you on the call, I don't have to explain to, it's MLIPs are really big, machine learning and atomic potentials for chemical simulation. They basically offer a shortcut to DFT. But there was kind of a fundamental problem before we even started this, which is that DFT itself was struggling to become really, really, really relevant, really powerful. It was used in like heuristic ways where people would develop trends, and then like there were actually innovations at Toyota that happened because of that. But it's a complicated road, and it's not really direct. For some of you may know the story also of like the materials project, working with Duracell and developing a product that actually now is on the market. But it took a long time to go from this kind of simulation framework, actually longer even than the traditional materials development timeline. So I think that part of the reason this stems is because, atomic simulation itself has a lot of foibles in becoming relevant in the real world. And you have to deal with things at much longer length scales that are capable of being simulated. And those are all things that AI can help with, especially now that we can write AI generated code and like kind of say, well, now I want to talk about longer length scales. How do I connect my, atomic scale simulations to the longer length scales? But it's still very much an evolving process. And part of the problem too is that practitioners of the engineering that goes into the car, at least in the automotive industry, aren't necessarily fluent in everything that the simulation tools can do. And so there's a big kind of, I wouldn't call it an education gap as much as an awareness gap and stuff like that. So that's something that that's part of the reason TRI exists, for example, is to try to see where these things do make sense.
Corinne is interesting hearing her opinion, but let me just a quick follow-up. You said that there's a gap. Is there a trust gap as well? So what do you need to demonstrate so that other parts of the company actually trust what you're saying?
There's a trust and a capability gap, I would say. So there's some, I mean, DFT in particular, and all of the surrogate models that are based on it has well-known flaws. For example, the kind of canonical example of catalysis is it doesn't get the like CO binding site right. So there are some things that people know it's wrong in very specific cases, and for that reasons, maybe it's also not trusted. Another good example of the capability gap is, NMC, very, very basic, universally used battery material is a disordered battery cathode material, right? It has partial occupancy, and that's typically the way the crystal structure is described. That's very difficult to model. You either have to use cluster expansions, or you can use these kind of not heuristic methods, but like coherent potential approximations, all the other stuff. But
Right.
you can't directly simulate those types of materials that are very much a cornerstone of the industrial process. So those are two
All right.
examples. But I'm sure I'd love to actually hear what Corinne has to say about that, because I'm sure she has valuable insights too.
Before we jump to Corinne, sorry, Corinne twice, but let me welcome Alix to the panel. And Alix, sorry about the mix-up with the agenda. There's this magic 30 minutes missing.
No problem.
So if we could start with a quick introduction, if you could introduce yourself and just very briefly tell us what you do in terms of AI in Dow.
Sure. So yes, thanks, Ale. My name is Alix Schmidt. I have been at Dow, coming originally from Dow Corning, for 17 years now. My background is in chemical engineering and data scientist. So I've spent about half of that 17 years as an experimentalist in front end, high throughput settings, as well as more commercialization and scale up settings. And I have been about half the time as a modeler in both manufacturing settings and my current role, which is in our core R&D information research group. So we kind of function, we like to think of ourselves as the IT for R&D and the R&D for IT. So managing all of the data architectures that support the work that Dow's R&D function does across our tens of labs, tens of thousands of products. as well as leading the way as far as materials informatics, what kind of infrastructure, what kind of technologies, what kind of skill sets and tools and upskilling we need to do to create that digital transformation across the organization. So I'm now a senior research scientist, the technical lead for the data science group in that area. I work on a lot of machine learning operations and upskilling programs, but my research area is in formulations, optimization, and the combinatorial problem of predicting soft matter behavior.
That's an excellent introduction. It actually begins to address our first question that we were discussing when you joined, Alex, and that was, how is industry and for what purposes is industry using AI and data intensive tools? So let's jump to Corinne now.
Yeah, so my group exists much like Alex does, also at the interface between R&D and IT. So we get used as the translators a lot as well. In terms of the gaps in and kind of what we're doing to fill them across AI and automation. Our businesses have and the R&D teams that sit within the businesses have the context for the products. They have the problem statements that are needed, but they don't always have enough knowledge or understanding, whether it's computational simulation or data science or an ETL pipeline, to know what they really need. So we function as a kind of single point of contact where they can come to me and say, this is the problem, and I can say, okay, we're going to scope that over here, or we're going to send this over there. We do some data model architecture. Actually, interestingly enough, I was just given responsibility for the analytical lab and for the kind of LIMS platform at Solventum, which is finally exiting 3M, so that all of this comes together under one umbrella to make sense kind of for the future. Being a new entity, we have a chance to reset in a way many enterprise organizations don't. So that is nice in a lot of ways. We do a fair amount of formulation optimization, and maybe to kind of use an example there, when you're dealing with formulations that are being commercialized in this day and age, they're not simple, right? It's not like these are 5-component formulations. If I'm talking about a dental composite, it might have 87 components, believe it or not. And as a regulated industry, we have to not only classify all of those components, but all of the impurities, anything that might leach out under a range of solvent conditions to all of the regulatory bodies. So if I break down that problem statement and kind of like, what are the gaps? Well, our formulators, even some think in ladder space, as I call it, where you change one variable and look at it. Others think in DOE space, which is more comprehensive, but they've got a complex multivariate problem where a human cannot process all of the inputs and all of the performance outputs in a way that's meaningful. So if we can visualize that, if we can streamline that, we often spend a lot of time with PCA analyses, trying to show folks the design space they actually covered and understand why the model's making recommendations in different spaces, because it's so complex to visualize that it's not that they're not smart enough to figure it out. It's that it's hard to wrap your head around it the way people look at it in Excel files today. And so we bring education along with somebody hands-on who can do the work to support them and sit with them through that transition. When we have enough users in a given space, we'll build a tool, an internal application that surfaces the models, that allows super users to put in their own constraints. And if we get beyond that, if we think we're going to have tens of users or dozens of users, then we'll find a package we can buy so that we don't necessarily need to support it and justify it as something that sits over our R&D kind of IT landscape. So that's kind of how we think about addressing the gaps. But it's different in every portfolio within every business in terms of where they're at, in both in the data they have, in how they're thinking about it, in the capabilities they have. Some businesses have a computational engineer, some have a data scientist, some don't, right? So we try to meet all of those internal customers where they're at to help fill the gaps. And I'll kind of end my answer there and note that Jen just joined too, Ale.
Yes. So welcome, Jennifer. Sorry about the mix-up in the published agenda online. If you could start, as we all did, with a quick introduction. We'll get you caught up on the discussion. We're just beginning with the first question, and the good thing is we have almost an hour left in the panel. So, Jennifer, go ahead.
Yeah, thank you, everyone. Thanks for the invitation to be on the panel. I'm Jen Schumacher. I'm a lead research scientist in 3M's corporate research labs. My formal training was in bioengineering and neuroscience, which I've now translated into AI. I've specialized in developing machine learning algorithms to support product development at 3M, and it's across multiple domains. So everything from optical materials, abrasives, adhesives. I used to work in healthcare while that was part of the company. So it's been really fun to apply machine learning to lots of different domains.
That's excellent. Maybe you and Alex could comment a little bit on the first question, or expand on the first question, which was how and what is being used in industry in terms of AI and data intensive tools, and maybe address. So Joseph was talking about, there's issues with AI, and there's also issues in terms of the data that we generate, say, from DFT, that has intrinsic limitations. And I was wondering, that's one approach, and that's an approach that's widely used, whether there's efforts to bring in legacy data and digitize that legacy data, make it AI ready, and use that data with AI to make decisions moving forward. What are your company's approach?
I can start, I guess. So it's interesting to think about the depth, where the depth of the challenge lies. So what we see often in materials challenge problems in academia, excuse me, is more around, we're going to study this particular system. We're going to get tens of thousands of simulation points or whatever so that we can make a really high quality model. We're kind of scaling in a different direction. Instead of going deep within one material class, we need to figure out what tools and techniques scale across a breadth that has very little data, right? So when we think about our products, we have tens of thousands of products. We're not typically modeling the properties of the products and materials themselves. What we're trying to model is their performance in our customers' applications, right? And because those are market driven, that Y variable of like what you're trying to go after in your model is just vastly different across there. So instead of having one model that can all of a sudden, do 25% of your business, it would be 1,000 models, each covering a tiny little portion of the business. And so we're really interested in technologies from our perspective, both from data collection and the data model itself of how can we describe things so that we can group more things together, but also in the modeling technologies around what techniques require the least hands-on tuning, right? What is the best out of the box? What is the best zero shot? Because we're just never going to have enough data scientists to go and make the absolute best model for everything. There will be a few areas where that makes sense to do. Catalysis is a big one, obviously, but to really impact the business at scale, we're looking at scaling the technologies, scaling who uses them, democratizing some of the skills. And that's kind of the approach, at least that we're taking at Dow, as far as incorporating data-driven decisions into our workflows.
Yeah, and Jennifer, you were talking about the fact that in some cases, at least, you actually make custom models, right, for specific needs 3M, and maybe you can expand on that.
Yep, as much as our management wants one algorithm to rule them all, that's just not possible yet. So yep, we're, in R&D, it's high variability. So we have a high volume of really novel things. So I think it is a lot of custom work, and where there are opportunities to democratize things like Alix and Corinne were talking about, absolutely jump on those. I think a lot of our automation efforts are focused on areas where there is some more reputation or standardization. So characterization is maybe one area where it makes the most sense to do a lot of automation. But a lot of that is still very complex for polymer systems. So a lot of work still remains in that domain. More generalized tools, so like for coding, for, and this is computer coding, not material coding. I try to be careful of that distinction. And like chat GPT type tasks are, we have tools for those in our enterprise level. So I see that's more where AI is, being used at a large scale, and much more custom, more in the R&D domain, product development domain.
Yeah, that's very interesting. So maybe we can move on to the next question, which has to do with autonomous labs. And maybe I was wondering if you could discuss to the degree that automation is being used. And this doesn't necessarily mean physical experiments. It could also be that you automate the generation of computational data, but as opposed to running simulations one at a time from a command line, like when I was a grad student, our ability to delegate some level of decision making to the AI systems and some level of automation. And so to what degree that's being done, and how is that changing the skills that are required for the workforce? And anyone can jump in.
Yeah, I'll jump in and start because I think this answer surprises people in that, we do a ton of automation. Very rarely do we automate with AI. Existing within a healthcare workspace, we're always aiming to automate, but we have to justify what we automated and the decisions we make to regulatory bodies around the world. Therefore, rules-based systems win the day. So we're absolutely automating data pipelines and how we process the data that comes out of our analytical lab and feeds toxicologists doing the analyses that we need. We're absolutely automating sample preparation within our analytical laboratory in places where those systems are commercially available, to the extent that we can automate more and more the mechanical testing or the standards that we need to meet. We do that, but those equipment and instruments do have to be able to handle a wide variety of our products, right? So like one day they might be using a load frame to measure tensions on a dressing, and the next day it might be a dental composite, right? They might be changing load cells or other things, but it's hard to fully automate those things with different form factors of products. So we use more and more the same coding tools Jen was talking about, right? Anyone who writes code, computational engineer, data scientist, everybody uses GitHub Copilot. I think that's pretty standard. We build our ETL pipelines. We have standard workflows like in AWS accounts most typically for any of our data processing, but we do that in a rules-based way. And if we're using a model to predict kind of where we should go next or what we should kind of think about expanding the design space or filling in gaps, then we write all of that down, and the subject matter experts still review that and make the final calls with the justifications.
Anyone else cares to jump in?
So I think it's really great, and especially the regulatory compliance things it's just like a standard that most I think people don't realize is as high as it is. That it's just really hard to fulfill. I think even when that's not there, and in Toyota it is there obviously with customer facing products and things like that. But sometimes we like prototype manufacturing related things, and Toyota's actually been experimenting with automated labs for decades, and the conclusion consistently has been that human flexibility trumps the investment that you make in any sort of automated capital for lab automation. Now, there's something that's very different today that is, kind of forcing us to reevaluate that hypothesis, which is that robots are much cheaper. Right? Robots are so much cheaper today than they have been. And there are like new ones coming out, like basically the pace of robotic acceleration is really fast. And that programming robots is also cheaper. It doesn't necessarily require the same type of upskilling because of LLMs, because of, all this other, all the just available information. But there's two things that I think are still important. One is that robots are lacking in many ways. There's a huge TRI, our robotics team, which I'm not on, but our robotics team, which I like to brag about, had this huge achievement of like generic large behavior models. And the upshot of that achievement was that they had a robot that could like cut an apple. And the cutting of an apple actually isn't even that. Like it's like, oh, it kind of cuts it like and it's like, ah. But the point is that like they taught a robot to cut an apple without like a lot of like intervention. And so that's actually like that's the frontier, right? It's not like a robot can really do like grinding on a lot of material science tasks without the rules-based programming that Corinne is talking about. So for Toyota, at least, the calculus hasn't quite shifted away from human flexibility being the thing that really can drive innovation in the lab, and for there being a need for that. I think there's going to be more and more automation that's able to be used, at least partially because this rapid prototyping is possible with the costs going down and with the programming costs going down. But there's still human beings who are amazing at solving problems in the lab, and it's a tough competition. So.
That's reassuring to a lot of the students in the audience, I'm sure.
Yeah. Yeah.
So Alex and Jennifer, would you like to expand?
Yeah, totally agree on the benefit of humans, but really proud of one example where we automated product design. So one area we found success is products where we're doing kind of mass customization. So for us, one of those things is optical films. And one of the complexities of that is kind of figuring out what nanostructures you're going to put on top of the film to make the light direct in the way that you want it to. And that's really hard for a human to figure out how to do. Like Corinne was talking about earlier, there's just so many variables you have to counterbalance to figure out what shapes are going to make the light, transmit or reflect at, the wavelengths that you want and what polarization. And there's a bunch of other variables. So we were able to come up with a physics-informed generative model that the user will put in, how they want the light to behave. And then we generate the nanostructure that they need to put onto the film. And so that's been great working with our manufacturing team. We can add in manufacturing constraints so that they can physically make it. And then it takes a lot of workload off of them to come up with it. So now we're just able to address a lot more products, a lot more customers. And it frees up the humans to say, what could be possible now, instead of, oh, what can I figure out, to design on a film and try it out and see if it worked or not. So we've seen some success with that, which is really exciting.
Yeah, I'll just agree with everyone that for the most part, at least with the robotic technology of today and backwards, robots, and I'm most familiar with high throughput research, combinatorial chemistry setups, are really good at doing the same thing over and over again. That's like the whole point of automation. But sort of by definition, in R&D, we're always doing new things. And so that has been a little bit of a disconnect that I think has limited automation's impact really broadly. Again, in specific focused areas, like Jennifer just mentioned, big impact. But it's not like we can say, okay, automation of our experimental design, is the number one strategy for all of R&D. But I will also highlight one other thing, getting back less to physical workflows, but to the simulation workflows, is we do have some nice success stories around Bayesian optimization. and guiding the decision making around simulation workflows to really get much more quickly to the insights that we're going for, to where those tools, the simulation or different kinds of computational methods themselves, may be applicable to more situations than they had been in the past. So one of those kinds of things where there's definitely a little bit of a human art to it, but it has less of that physical challenge of like, okay, now, the optimizer says to run something that's, 100 times the viscosity. We have to like physically go in there and adjust the equipment. That slows things down. But I think there's a lot of opportunity in the simulation space to have more intelligently guided loops there.
That's very insightful. So I have one more question, but there's a question from the audience that I'd like to bring up. So Abdul Jabbar, would you like to unmute yourself and ask your question? Because I think it's a nice follow-up to the discussion we've been having. If not, I can read it.
Yeah, thank you. I'm not sure if you can hear me.
We can.
Okay. So my question is about in material processing, data is usually generated within a tight operating window. So how you will build an AI model that can generalize if it is basically we are not exploring the parameter space here.
Yeah, so that's great. And so a lot of the discussions we've had so far has to do with industrial research. But how about using AI in a production line, in a plant where you're really hopefully not changing things too much?
Yeah, I could speak to that, having worked in that area for about 5 years. You're exactly right. Yeah, there's this fundamental difference between an R&D setting where you may have a lot less data, but it's a lot more enriching to a pattern recognition approach because it has that high variability. Whereas in production, you just don't have that. And there are attempts to do things like hybrid models with first principles that can kind of extend the range of some things, but it's challenging for sure. I mean, that's really hard, and there's quite a lot you need to know about the process, and are you operating within the assumption set that model applies to get those kinds of things to work. So typically in a production setting, you're also not trying to learn how to make new things, right? So the goal of your modeling is often different. I don't know necessarily what your question was directed exactly towards, but in that case, you usually are more interested in sort of anomaly modeling, right? Like let's make a model that includes all of the acceptable ways of operating the process. That way we can be told when it's operating in an unacceptable way. And so that's just a completely different modeling goal. And so it meets the needs of that organization. But yes, when you look around and say, man, I really wish we could learn how to make different types of products. And wow, manufacturing has a lot of data over there. Can we use that? The answer is usually not really. Does that answer your question?
Yeah, that answered. Thank you.
Okay.
Yeah, that's great. And so I'll let you answer. But so are we? So for example, in the manufacturing plant, can you do feedback loops where you tweak parameters because of models that you developed in a research lab that I see this drift in my line and I can correct it this way, or these are tolerances where I can build on models that I created over a larger space, this design space, variable space, to keep things within the constraints that I want in the plant. So sorry to interrupt, Joseph.
Oh, well, to that question, it always depends, right? Like it depends on how like the manufacturing is organized, and it depends specifically on like where the human is, right? So that to me, one of the things about getting AI manufacturing is that like you have to experiments like and I mean experiments in the very abstract. Changing something and seeing what happens are incredibly expensive, millions of dollars, right, to shut down a manufacturing line for even like minutes or like hours or things like that. And you should do it, right? Like if you have a reasonable expectation of gain, you should still do it. It's rational too, but you have to convince the people who are accountable for that line that it's worth doing. And so you better have really, really solid explanations of why you believe that something's going to happen. And AI doesn't always have that, right? That's kind of one of the foibles. It's like why are we doing this? Is it just because of a model prediction? Is there a physical reason? Do we have a physical model that says something like this? Because the human being has to be convinced. Because if they shut down the shut down the line, and then like the company loses millions of dollars, it's their head on the line. So anyway, strong reasoning traces can help with this. Physical models, I think, tend to be more persuasive than kind of like what I would call like overly black box models. And so those are things that I've used in this particular context to say like this is why you should make this change. But at the end of the day, it's always got to be the person who's in charge of the lines decision who actually has the full picture. So I'll just stop there. That's because I'm sure other people have more intelligent saying things.
Thank you, Joseph. Any additional thoughts, Alex or Jennifer? And we can jump to the next question. I'm sure we'll keep coming back to these topics. Or Corinne, I'm sorry.
I was going to add one thing, which is, I think what that question is really aimed at is what I would call pilot scale. So, we try not to interrupt manufacturing to Joseph's points, but we do have pilot lines where we can deploy models and PLCs and things that run them to sweep parameters as quickly as possible. And we, for example, are building one line that represents, where we can switch the modules to represent 10 or 20 different lines in our manufacturing footprint so that we have all the right historians, all the right data analytics that we can look after the fact, and we can both proactively test models. But to Joseph's point, if you have a line like this and it's deployed on the right scale, it can be production equivalent material, which can be immensely helpful. You have more flexibility to deploy the automation or the AI or whatever that means to get your justification for saying manufacturing, this is why you should do this. And we're trying to build that out new. I know from my time at 3M that they have some similar capabilities, but that pilot scale is really where the two meet, right? Like I'm never going to deploy a model in manufacturing. Let's just be clear on that. If they're going to do that, they have a group that does that keeps track of all like the IT considerations because they're different in manufacturing than they are within the environments that we work, along with the kinds of, what needs to be true because I'm making real product on the line from a regulatory perspective.
Excellent. So let's move on to the next question. And this to me has to do with the raison d'etre, pardon my French, of MaRDA, okay? Pardon the pronunciation. This is how can academia and industry work better using better data management, using more modern tools for data. So academic research can actually be used to generate insight, or to provide actual data that industry trusts enough to bring it inside the fence to build on their models. So that's one aspect. Okay, so the data that we generate, the processes that we generate in academia, what can we do to make those more useful? And the other side of the question has also to do with something in a question asked in the panel by Viswanath, which is, as much as we think in academia that we're genius researchers, the main product is students. Okay, that's what we do. And so, what are the skills? What are you looking for in future employees in terms of skills and fundamental knowledge in this very rapidly changing field? Sorry. Anyway,
I could go. Around the data, it's really challenging because, like I mentioned, the places where our models are most valuable in accelerating the time from a need to commercialization of a product is really in that end stage where you are very aligned to a specific customer application test. Sometimes those are ASTMs, so that could be good. That could be a way for us to bridge some different places there. But sometimes it's like there's no industry standard for what this thing does and how we compare it to what our customers tell us it reflects in their system. So we have found it quite challenging to take data from academia and apply it to our models, just because it is so much further back in the sort of descriptor space that we're studying. I think there's one exception to that, which would be image analysis is something that has become so trivially easy, but can capture so much more of the real system and what's really happening. And so, yes, you may still not be working on, the exact way that we're having our products work within a certain application, but having techniques that are image-based or multimodal or whatever it may be, I think is a direction that things can be moving that will help us bridge that gap between techniques made elsewhere outside of industry, but that we can actually just pick up off the shelf and leverage. I have a lot more to say about the skills as well, but I'll let everyone else check.
We'll come back to you when we talk about skills. How about that?
The one thing I'll add in is that, the research is really, de-risking foundational knowledge for industry, and that's, greatly appreciated. So don't stop doing that. I think that's really critical. And if you want to be closer to industrial applications, we've had some successful collaborations where, we can help focus specific research areas of things that are applicable to industrial problems, but there's still a ton of work that goes into translating that into the industrial setting, which, I don't have great answers either. I think Alex said it well about, the problems and how specific they are once you get into industry.
Yeah, but I like the concept of de-risking technologies.
Absolutely. And we value that a lot.
Yeah, and we still use all of the, I would say, publicly available, like standardized measurement data, right? So much of it we can get in Abacus or ANSYS today if we need, the heat capacity of a given polymer, or if we need the, average modulus. If we're building, simulations on the front end of new product development, our businesses will come to us and say, this is the change we want to make in a current product, or this is how we're thinking about the other product. And we'll use those physics-based simulations to say, okay, given the literature results, these are the kind of failure modes I would think about, right? So that the product developers can refine and kind of address those earlier on in the process. So absolutely all of that like standardized data is helpful. I agree with Alex and Jen that most often like these large data sets that are being stood up we haven't seen yet good ways to use them. But certainly I've been part of a number of different kind of industrial university partnerships where part of what we're trying to do up front, everybody hates the fight over IP. That always happens. We try to set up the master agreements so we work well together. But I'm very encouraging of us outlining from the beginning what the data formats are, what the code documentation is, all of these pieces, so that there's a common understanding of like what the transfer is. I have one project going right now where like it is very niche, but like I need that data set. And like I did not have a way to get it internally, but I knew a professor who had the access, who had the students, who could turn it into a master's thesis, and I'm very happy to kind of pay a university to do that. Now, it is ultimately about trust, because that is a data set that we don't want accessible to our competitors, right? Like, we are paying for it for a specific reason. We cannot find it, right? So those are the pieces we have to work through, but I think we can do better getting to a common language on what do data formats look like for data sets that are being transferred, what do code packages look like, all of that.
Yeah. Joseph?
So there was a lot of talk about FAIR yesterday, findable, available, interoperable, usable, the standards, FAIR standards for data. And I think available is actually like the biggest problem in our field. A lot of stuff just isn't available. It just like Corinne just said, it's like this thing just wasn't available to me. And so I hope that people are able to make data more available. Something that I also think I hope can become more true is there's a lot of data formatted out there that isn't particularly well suited. It doesn't have what I call machine sympathy. Like it's not really well suited for ingestion or reuse, and reusable maybe is a good, part of the FAIR thesis to like apply to that. And I'll give you an example actually. So Toyota published all this battery cycling data, I want to say like 8 or 9 years ago. And the data blobs are just huge and they're all JSONs. And like, that's not an efficient way to store floating point numbers, right? Like you should have something much more like byte compressed and like something much more like, compact if you're going to really feed, many terabytes of battery cycling data into like a machine learning model. Because otherwise you're going to have to like house it and all this other stuff. It just takes time to like shuttle it back and forth. So like, anyway, I think people thinking about the performance of their data formats for machines, reading them and using them is something that we could do as a community more. Can I start the skills thing? I guess like we
Go for it.
So something I think that is important for at least me to do here is I think we should be humble about telling academia what skills they should bring to their students, because one of the most valuable things I've found in hiring new people is that they know a lot of stuff that I don't know about, right? Like, and they like academia has trained them in all the new and the latest and the greatest, academically interesting things. And industry can teach, like we can teach them the things they need to know about Toyota for the most part. It's not like they're not coming in with basic things that are valuable, but the fact that they're changing the way we think by having new ideas and new ways of doing things, I think is probably the way to go. So I don't want to say like academia should change much, but maybe even lean into its strengths of like actually educating students with new ideas and new ways of doing things. That's what I would say it should do. So
Thank you. Who else? Alex wanted to jump in and come back to the skills.
Yeah, I think, in my opinion, the skills has been by far the more valuable of the outputs rather than a particular data set. Getting that student who's now an incredibly productive employee is really important. And kind of a little bit to Joseph's point of part of our upskilling and digital transformation strategy is just sort of this reliance on the fact that newer people will be using more current and up-to-date techniques of various kinds. So, for example, 10 years ago, you had maybe some researchers programming in Fortran or VBA or whatever. And nowadays, high school students, like large numbers of high school students, are learning Python to a degree that would have been impactful in a lab setting. And so we see those accelerations and those things happening through that injection of younger talent there. The one thing that I would say would be really helpful, sort of like the cherry on top, if we could also get this, is sort of this, and it depends on your role too, but this difference between doing something once, even if it is via code, and putting something into production, right? There's an enormous gap between those two. In research, we typically think of, I've done this once, the code it's reproducible, it's transparent enough for FAIR practices or to submit the code to the journal, whatever, but that's not the same thing as this is a system, which if I was to deploy to users and maybe it's receiving new data, it's maintainable. Corinne mentioned earlier, custom apps and sort of this overhead of, what is their value versus the cost to maintain, because code does go out of date quite rapidly. Those are real considerations, especially when we take the democratization approach that I mentioned. So just some best practices more from the software development standpoint of, like Corinne mentioned, like standard ways of doing packaging of things, of documentation of packaging, good Git behaviors, and understanding code collaboration and version control. I have a lot of work in the MLOps space, which is basically just extra steps of version control, because you have to version control the code, the data set, and the model artifact simultaneously. Those things, I think, can make the difference in the success of a new employee, from being somebody that generates amazing insights to somebody who generates amazing insights and is able to convert them to, dollar value. So that's, one thing that I would think about, and is researchers and physical scientists and things like that didn't used to have to be software developers. So it's a new thing for sure. And some PIs might not be necessarily familiar with it, but I think it's important that we use that injection of new ideas to get that practice up and going.
I might quote you on this, Alex. I couldn't agree more. Okay, this is music to my ears. All right. Any other thoughts, Corinne?
I'll just say that, like, I agree with Alex, and also this is still a work in progress. So, don't think that like students don't have a chance if they don't know these things. I actually, one of the things I want to see is that if folks learn these digital kind of skill sets, that they not lose their subject matter expertise, right? So one thing I don't typically do is hire computer scientists, data scientists, because we work with the labs, we work with manufacturing, we work with quality. We have to be grounded in the actual physical what's going on. And so that training and that expertise is immensely valuable, along with the digital skill sets that they bring. The one place that I have an exception for that is I have 2 software engineers and cloud infrastructure experts who run all of the pipelines for everybody. Like, they are our team's gate. If you are going to deploy a thing internally, they make sure we follow all of the IT rules, everything. They're the last call on code reviews and things like that. So at this stage, we need people to understand that just because you built it doesn't mean we can deploy it. That doesn't mean it might not be useful in early stage work, but like, we got to build those competencies over time. So just so that folks know that, like, we're not all the way there yet either, right? It's not like those are formal requirements, at least not that I'm posting in kind of job descriptions and stuff like that. But certainly it can be the differentiator for folks today.
And to your point about it, it's not settled, right? Like, MLOps is like a 5-year-old industry, right? So I think what the stack is, like the specifics, like when job postings post specific packages or whatever, I always find that a little bit suspicious. Because again, that could be an exact place where there is a better way to do something, and we would love to hear about a student's experience in school. But it's more about the principles of, like, what is the difference between a POC kind of project and something that's ready to go to production.
Yeah, I like that conversation, and I think this is something that in academia and also in industry, with these agentic systems and reasoning systems that allow you to almost to with research ideation, with coming up with solutions, they're amazing, right? And I'm amazed, like all my colleagues. At the same time, you can get 10 different answers if you ask the same question 10 different times, right? And so I think how do we balance this amazing technology with the ability to generate results that are reproducible, that are production ready, that you can use to make a decision? So I think it's a fascinating topic. Anything to add on the skills and the fundamentals? If not, we have a few good questions from the audience. All right, so we'll move on. We have 2 questions from David Elbert. I'm going to skip you, David, and go to Rushik. because I know you have chance to ask these questions, and so if we have time, we'll come back to you, Dave.
No problem. No
Rushik,
problem.
go ahead.
Yeah, hi. So I guess my question was that recently, so a lot of tech companies who incorporated Gen AI suits into their like coding stacks and stuff like that have been noticing that there has been a loss of productivity in overall what the Gen AI produces since they have to debug a lot. So in terms of like scientific models and such, this becomes even further more important since there are many more caveats that one needs to consider. So, how does industry manage these guardrails in general while using these technologies?
So, I mean, I'll say that I'm not sure that we know how to use AI safely yet. I think it's another kind of humble answer, because it's so new and because I think we're also so in many cases the answer is not to, right? Like it's like we need to wait for this to be safe before we can use it. There's a lot to that. There's questions about like information security too and AI use and whether something's hosted on-prem or something along those lines. But sometimes the answer is you just don't use it until it's safe or until other people have proven that it's safe or until you're more convinced that it's safe or more convinced that I'll say in the only place where I really feel like we've made gains in like making like kind of trying to bridge this productivity gap because it's absolutely true. Yeah, basically anybody who's used AI coding knows that all sorts of bugs show up and then like uh, you have to sit there and like hunt for the bugs or something along those lines. So one thing that has helped in our experience with software development specifically is test-driven development. So you either write the test yourself or you like really have a tightly human coupled like cycle of developing the tests and test. And the thing is, this was kind of good coding practice all along. Test-driven development exists long before AI, right? So it's like you have all these strong priors. If you're translating for something, for example, translating code from one language to another, you can like have a bunch of outputs from the first code for the second code, and that tends to constrain the agent in a way that reduces waste, I think. In my experience, in my like I said, very limited experience, because we've only been using AI agents for about a year now, and maybe even less than that. It feels like longer than that. Anyway, the point being is that you have these strong things that must be true, and you guide the AI to fulfillment of those things, or test it on those things as it develops, and hopefully, then it also becomes easier too, because a lot of times when it fulfills the tests with stupid things, where it just like substitutes a variable, it's like, well, that's clearly wrong, and then you can give the AI more feedback. But I don't think this is a solved problem. It's just one anecdote.
Oh.
So.
But I think this is another area where industry and academia collaboration is critical, right? Because those studies are true that Rushik was quoting, but the students we're generating right now from academia are going to use AI for coding, right? And so whether it's better or worse, that's going to be the world we all live in. And so thinking about those fundamentals of verification, validation, putting those fundamentals of software engineering at the forefront, no matter whether the AI or the engineer writes the code, then you're guaranteed certain things.
There is a field of formal verification of software where this is like really like math
Definitely.
field day, right? Because they have these strong guardrails that can be formally verified by software, and they're able to make, I think, incredible use of AI because of this. And we don't have the same luxury, of course, because we have a much larger, I would say, like reasoning and rigor space to kind of fulfill. But yeah, I hope that we're able to get there in the same way.
It depends on what we're doing with it, right? So I was gonna kind of go where Joseph was indicating, which is like when we have software on our devices, right? As a medical device company, we have very strict standards that we have to go through V&V processes for, and even uncertainty quantifications for. So like in the most rigorous sense, those skill sets for doing that in software exist within, Solventum today. Now, obviously, as you start to use AI for kind of more general coding or for things that aren't on product or in product specifically, we have enough internal evidence to show that the more senior the software developer, the more they're getting out of it, right? And it's because they catch those bugs more quickly as they're going. So, we know that this will have to be true in the future. We don't limit who has access to GitHub Copilot or AI assisted code writing tools. We do try to push on the documentation front. right? And to make sure that we understand exactly what each kind of section of code is doing. And that means kind of code reviews, that means kind of having best practices sharing, but we're figuring it out as we go, right? Because we made these tools available to senior folks who wrote code, a couple of years ago and to everybody about a year ago. So, even our businesses that have software in the product are still figuring this out, but arguably have to meet very high software V&V requirements. And those of us who do internal development are using all of these tools and, kind of coming at it with that same lens, but maybe not held to the same exact V&V kind of rigorous standards, but we try to think about it in that way, right? Do we understand what all the aspects of the code are doing? Because if someone else has to debug it later, like we never want a single point of failure, even for our internal applications in someone's understanding of the code. So we try to make sure we share responsibility for the internal applications that we have and for the code repositories.
Jennifer, would you like to add to this? You mentioned building custom models in your company.
Yes, yeah, so completely agree with what Corinne and Joseph said already. And I'll add, and maybe going back to the skill set question, I think fundamentally it's so critical for, our workforce to have critical thinking and really strong experimentation skills, because that's how you're going to be able to validate whether a human or AI is writing code and doing the bug catching. So, with my team, I really work with them to think in all the ways that maybe the code could break or a user could be using this incorrectly to make our code really robust to a lot of different things. And, it comes down to code practices, documentation, making sure they're thinking about all the weird ways that this could actually go wrong. And that whether it's from AI or humans, it's just a good practice.
I'll add that I think we're not really existentially worried about it. I mean, I think every major technology leap like this, you see that hump at the beginning, the activation energy, where it is less efficient. But it's so clear that the end state is going to be dramatically more efficient that we're not worried about going through that. When I'm ever in doubt about if we're doing something in the right direction, I'll always think back to, from a chemical engineering background, what would the transition between a chemical engineer, like say a process design engineer, our role, hand calculating or maybe, I don't know if spreadsheets existed, but calculating in some way the differential equations to balance a process sheet, like that was your job. And then Aspen or other similar process simulation softwares come out and it's like, oh my gosh, what is my job now? Well, you still need to make the everything check out, and you still need to make sure that the problem the program is solving is aligned to the problem the business needs solved, and you still need such and such other domain things and checking assumptions and communicating your results effectively. So I think we're just in another one of those cycles, and very confident that once people learn the tool, right, you can already know how to code, but you don't know how to agentic code, right? So you need to learn what are the best practices. Is it the test-driven way, the best way, et cetera? We'll get there, and we're learning alongside everybody else. I will highlight one thing that it's really good for that is a huge time savings is the situation where a person has to take over somebody else's code base, right? So if we have like 1 million legacy apps, code bases for whatever thing that somebody made and then they left the company or whatever. There's just so many of those, and some of the documentation is good, but some of it's not that good. But the AIs are extremely good at figuring out what it is, what it does, why it does certain things. And so getting people up to speed on a code base of like, oh, I own this now. I need to be able to remediate it or uplift it or refactor it or whatever. That's already paying off very much so. So, we're very, very hopeful about the promise of this.
It's great. It's great to end in a hopeful note. We have maybe 4 more minutes because I want to leave 5 minutes before posters and make sure everyone can actually be at the poster session on time. Dave, do you want to ask one question, short question, short answer?
Yeah, sure. This has been a great panel, everybody. Thank you. This has really been interesting, and Ali, you've done a great job at sort of steering things around. So I think I was just going to focus then on this idea that, in academia, we focus a lot about reproducibility, traceability, and scaling, which are all things that you have touched on and must be critically important in industry, but maybe you think about differently. So I'm wondering how they're viewed, how they're implemented when you hear those words, reproducibility, traceability, scaling, what they mean to you. Nothing, evidently.
Well, we established that was very important, right? So I think Alix made that point that
Right.
don't write code for one time. Yes,
Right.
it has to go in production. So I think those skills are very valuable. So maybe they want to expand on that.
Yeah, I think, the comments about documentation, that's my first instinct, just for, creating that legacy. But the scale question, at least at 3M has, a significant meaning of, you're going from the lab to a pilot to a manufacturing line, and that's a ton of work and complexities that get built upon one another. So if you can have that strong documentation from the start, I think that only helps accelerate for each of the next scales.
Yeah, very good.
Thanks.
Last thoughts?
I'll say I think about this on the kind of simulation front as well as on the data science front. I think we're all still kind of pretty confident that if you give 100 engineers a problem statement and a simulation package, you might get 100 different answers. So one of the things that I focus on pretty heavily is, where is the use of those models? Where are they going to be reused sufficiently that we need to have that standardization versus where are we kind of providing insights in a kind of ad hoc manner that are meaningful, but it isn't, we're not going to face the same scaling problem, right? Because if we're going to reuse a model again and again and again for some specific purpose, then it's worth us taking the time to standardize on the methodology we're going to use. And it is slower going at first because typically you have to have somewhere between 3 and 6 people involved in agreeing to what that framework looks like, what the methodology is, what are all the risks, what are the assumptions. But actually you get a more rich conversation, right? Because when people have to write down all of their assumptions and you have to kind of think through them and what the risks really are, you end up coming out with something that is far more robust in the end. And so depending on what the purposes are, it may depend on whether or not we need that level of it. But I focus on that level where we think we're going to reuse it to really kind of enforce the kind of reproducibility and traceability. Whereas, if there's some specific small question that we just need to get answer and keep things moving, then that's how we're going to handle it.
All right. So
Thank you.
We're basically at time, but there's one more comment or question by Denise Easton. And so Denise, I'm going to let you, I think it's an interesting comment. So just let's leave it as a comment. And I know there's a question at the end. We're going to leave it as a rhetorical question because I know no one knows the answer to this question. So let's just ask the question and leave it hanging for next year's MaRDA meeting.
Thank you. Do you want me to ask it in?
Just ask it.
Oh, okay.
State the challenge. I think that's interesting.
Okay. I come from a complexity science perspective, working across many domains, but the statement was, as AI becomes more central to forward materials development, the constraint really is no longer just model accuracy or laboratory automation, but whether our interconnected and increasingly more interconnected academic, industrial, and governmental ecosystems are structurally capable of learning together. So we need to address coordination architectures, which go beyond technical, semantic, and governance frameworks, but that allow intelligence, and intelligence can include data, it can include research, development across institutional boundaries. So the question I had was, where does this responsibility for building coordination architecture lie? And at the same time, considering that we do need to allow collective learning, so collective learning ecosystems, and not erode competitive or institutional integrity. So I've been, each of these sessions has been so great, and I keep holding that question. So I hope I can be more involved over the course of the next year, but thank you all. This has been terrific.
We welcome you, Denise, to our community and MaRDA. So jump right in. And I think this is an interesting question. I'm sure some of our friends from the federal government and program managers have lots of ideas and actual programs on these, but it's a challenge. I think we all agree that this is something that we need to address. So I think on that future-looking question as to how we can all learn together and share and build an infrastructure, we'll close the panel. And I'd like to thank all the panelists and encourage everyone to go to the poster session. And I'm sure Selena can tell us where to find the link.
Yes, thank you, Ale.